Hello there, here's an exercise for some Year 13 further mathematicians doing the statistics module. Now look, we did some of this. These are sometimes called GOF tests, goodness of fit tests. So on the calculator very often you see this GOF. And the GOF test, or goodness of fit test, we saw in Year 12 further mathematics, and we were looking at whether or not we could fit certain types of distribution to the data that we then get. And we're going to carry this on now, and we're going to carry it on looking now at normal, binomial, Poisson versions of the same thing. So let's have a look. Now you may recall when we did it last time in exercise 6A, if you haven't seen the video, but I would suggest very strongly that you go and have a look at video 6A, because this is where it all starts. But when we did that, we did degrees of freedom was n-1, and that was important. Now if we do binomial, Poisson or normal tests, there are different numbers of degrees of freedom. So you kind of have to learn the rules. So for binomial, it's n-2. For Poisson, it's n-2. And normal is a bit weird. It can be n-1 or even n-3, depending on whether or not we know or we have estimated our values of mu and sigma squared. The ones we did last year were just n-1. So you need to know what type of distribution you're looking at. Here's our first example anyway. It says a Poisson example, so we know it's Poisson, and we know our degrees of freedom, it's according to just now will be n-1. But for now, let's just see what it says. It says show that the sample mean for the data is 0.37. What is it? It's the number of calls arriving at a switchboard. Okay, well I go into my Casio Class Whiz, and I go into that menu button for one-var stats. So I'm going to do it here now. One-var stats. Right, and so I have to enter these numbers. So I put into the list that's got an X at the top. I put 0 and 1 and 2 and 3, and they're the 4. They didn't get any, so I don't care about those. And then into the frequency column, and if you haven't got the frequency, you need to enter it so that you can see both columns. So a frequency of 71, 23, 4 and 2. And once you've done that, you can press the option button, and then you can press that you want to see the data. And so I'm doing that now, and I want the X bar, and here it is. It's 0.37. So it's exactly right, in fact. So it says show that the sample mean is 0.37, and I haven't really done it in terms of, but as far as I'm concerned, we get 0.37. If this was an exam question, I might want to show some working out. It is believed that the Poisson distribution is a good fit. Okay, so they're saying X is Poisson, 0.37. That's a note on this. And it's a good fit for this data. So what we have to do then, if this is the observed data, we now have to work out the expected data. And we're going to have to do that using this Poisson distribution. We're going to have to work out the probability that X equals 0, for instance. We're going to have to work out the probability that X equals 1. Probability that X equals 2. Probability that X equals 3. And although we got 4 or more, we got none. I suppose we're going to have to do the probability that X is greater than or equal to 4. And we do that using the we can use I'm going to use my I've got a Texas calculator here, and I'm going to use Poisson PD. But you could use a Casio Class Whiz in the same way as I was just using it just then. So we're going to go to calculate some Poisson probabilities. So again, menu, go down to the statistical one and choose the Poisson PDF or PD button. And when I do that, Poisson PD, and my lambda is 0.37 because they've told me that, they calculated that. My X value is 0, and I've got a value of 0.691. I suppose I could be a bit more accurate, 6907, and I'll get better answers if I use that 6907. Now I'm going to just chuck these all in my calculator and see what I get, and then I'll pause the video until I do that. So this is what I got when I've typed them in. And of course, these are probabilities, so we're going to have to do some work on them a bit. And the last one, by the way, you have to do this as using the Poisson CD, or depending on what calculator you're using, maybe a CDF. So this is 1 minus the probability of X is less than or equal to 3, and that's the critical thing. You need to put a 3 in there. When I've done that, I've got 1 minus 0.9994, which is really small, 0.0006, got there eventually. Now, as I say, these are not frequencies, these are probabilities. So to get the probabilities, we have to times by the number of things up here. If you add them up, they add up to 100, luckily. So I can times all these by 100, and I get the frequencies. And this is on 69.07. This one's 25.56. This one's got a very small 4.73. In fact, these are all quite small. This is 0.58. And this one's a ridiculous 0.06. So now look, we're now going to want to do a GOF test on this, and that's what this is. It says, test your hypotheses. I suppose our GOF test will start off saying H0. The data can be modelled by the Poisson distribution. And it's very common to have to write that kind of distribution. I won't write it all. And H1 is broadly the same thing. The data cannot be modelled by the Poisson distribution. So you just get into that habit of modelled by the Poisson distribution. So you get into that habit of just writing those out and getting used to the fact that you're effectively going to say it fits or it doesn't fit. Now, when we've done this, then we're now going to have to work out our chi-squared value. And to do that, we need to write in list 1 we put our observed data, and in list 2 we put in our expected data. Now, the one issue I've got is here, and it actually says in the question, remember the expected values must be greater than 5, and these three aren't. But we can combine them, and between the three of them they will be. So into list 1 I'm going to type in, well, list 1 of course is the observed data, 71, 23. Because I've got to combine these, I've also got to combine these three, they add up to 6. List 2 will be 69.07. 25.56, and what do they add up to between them? So let's just do that quickly. 4.73 plus 0.58 plus 0.06 adds up to 5.37. So it just about sneaks over the 5 rule. So I'm going to enter these into my calculator. Again, on the Texas calculator, I press stat, I go across to tests. Well, first of all, I need to edit it. So I stat and edit. So I need to put my numbers in. So list 1 will say 71, 23, and then 6. Just those three numbers. And then in the right-hand column of that, in list 2, 69.07, 25.56, and 5.37. So now my data is in. And now I can press stat. I go across to tests. Let's do that again because I did that wrong. Let's go start. And I go up to the chi-squared GOF test. And it says that L1, L2. In actual fact, the degrees of freedom here should be 2. Mine said 4 for some strange reason. But that doesn't really matter. I go down to calculate and I press enter. And that's really what I care about. I care about what chi-squared is. And it says chi-squared, from my calculator, is 0.384. I have no idea if that's right or wrong. Seems very low. And I suppose it's very low because these numbers aren't that dissimilar. They're very close, So so I now need to work out what the critical value is for this test. Oh, it's kind of funny. Critical value for this test then. And no, obviously we've got 3 sets of data here, 3 categories if you like. So with a Poisson distribution, if we just went back to that, it says Poisson, you do n minus 2, and that's because we have this lambda as well as the totals. So n minus 2 is 3 minus 2. So we've only actually got, this is actually degrees of freedom I'm doing here. Degrees of freedom is 3 minus 2 equals 1. So when I find my critical value, I've got to use 1. Does it say? Yeah, it says 5% significance level. So if I look at my table says, now for 5%, I have to look at 0.95. Degree of freedom is 1. You can see it just under there, 3.841. So my critical value is 3.841, which is, it looks very similar, but they're obviously much different. Here I've got chi-squared then is obviously much less than the critical value. And when it's much less, I reckon, right, do not reject H0. It has to be bigger to reject H0. And so effectively I'm saying the data can be modelled by the Poisson distribution. Let's see the answers. So 3.84, 0.384 and 3.841 for the critical value do not reject the null hypothesis. So we've done it right, and that's the correct working out there. So I'm pleased with that. Now we've got another example here. This is the binomial example. I think in total there's 3 or 4 examples. We're not going to do them all in this video. We'll do some in class. So this says we've got some data which we think is binomial. So by finding the sample mean, find an estimate. So the estimate is 0.2. So we got a similar question to last time. So we have to put this into our Casio calculator and do 1var stuff again. So we did that before, so hopefully you can remember how to do it again. Into my calculator now. 0, 1, 2, 3. And then the frequency is 44, 20, 8 and 3. And then we want to find what the is using the option button. And I get 0.6. So I get the sample mean to be 0.6. And I suppose if that's true, remember for the binomial distribution, mu equals np. And here I've got n is 3. So effectively, using x bar as my estimate for mu, they both represent the mean, I can say that 0.6 equals 3p, and that implies therefore that p equals 0.6 divided by 3, and that is 0.2. So yeah, it seems then that this is x is binomial 3, 0.2. That's really what all that stuff was about. And it says, show that at the 5% significance level, there is evidence that this binomial distribution does not fit the data. Well, what would I do here? First of all, I would be writing my hypothesis out, H0. The data can be modeled by the binomial distribution. And these are important you write these out, because there's a mark for probably for the pair of them. The data cannot be modeled by the binomial distribution. So that's very quickly written those out, but you'd have to make sure you get all the marks for that. And then of course we need to find our chi-squared value. And we find our chi-squared value by first of all finding our probabilities that x equals all these values again. Now what did we have? We had 0, 1, 2, 3. So that's what we're going to have here. We're going to do probability x equals 0, probability x equals 1, probability x equals 2, probability x equals 3. So I obviously need to type these into my calculator using the binomial PD button to work out these probabilities. I'm going to pause the video and do it now. And there are my probabilities. And I notice this was for binomial 3, 0.2. And if you add up all those probabilities, they actually add up to exactly 1, because these are the only possibilities, because you only did it 3 times. Now, how many times did we do this experiment? We did it, if you add these up, 75 times, 75 packs of bottles. So if I times all of these by 75, I'll get my expected frequencies. Again, I'll pause the video now. And here are my expected frequencies then. Now, the first thing I notice is this one is under 0.6, is under 5. So I'm going to have to combine these, a bit like I did last time. When I do my GOF test then, I'm going to have my observed data in this one, and that's going to say, well, let's just go back and see the data, 44, 20, 44, 20, and the last one when I combine it was 11. And when I do my expected data then, I can now write 38.4, 28.8. When I add those together, I get 7.8. So I just typed this into my calculator in the GOF test section, and it did give me this value, 4.82 for the chi-square. Now, of course, I had 3 categories. 3 minus 2 for the binomial means my degrees of freedom is 1, and it's a 5% test, so my critical value, according to me at least, is 3.841. Now, my chi-squared is bigger than the critical value, so I'm going to reject H0. And let's see what my answers said. And you reject H naught. Yes. Now we're a bit rushed at the end. We'll finish this and we'll finish the last question in class. So thank you very much.